All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are gonna carry on learning about Google AI Studio and how to use the Gemini API. Give me a second. Let me turn this other thing down. Okay, uh, dude, I'm kind of glad that I've had the chance to stream to do a talking stream, both yesterday and today. Today I'm probably only going to be able to go for like an hour maybe, but like that's still good. Maybe after that I can eat something and then start up a mute stream where I'm either going to continue reading up on Google AI Studio and the Gemini API, or I'm gonna go through that ML crash course and see what information we can absorb from it. The good thing is that that entire course, it has a whole lot of theory in it, and then at the end it has the practical stuff. So they give you like collab notebooks, Google collab notebooks. By the way, I've just never touched Google collab. Like, I've heard of it, I've opened a couple of those books, those notebooks. From what I understand, it's kind of like Jupiter, where you have a server that's running and you can set up notebooks. Within those notebooks, you can have code cells and markdown cells, and that way you can have modular code. You can have these code blocks that you can run whenever you want. Basically like what we're able to do with Kaggle notebooks. So I'm assuming that's mostly it. But yeah, I haven't used Google Colab a whole lot. I've seen it mentioned in a bunch of different places. Maybe at some point I should look into Google Colab as well. The thing is, I don't have too much use for it unless, let me check. Let me check if Google Colab provides like computing resources in some way. I haven't looked too much into it. Google Collab. We'll get to the. Wait a minute. Are we live? Yeah, we're live, but my feed seems to be stuck. Give me a second. Let me just refresh my stream manager, and I'm loading up Google Collab on a different machine. Oh yeah, okay, we are good in terms of the video feed. By the way, I've been considering. Oh wait, hold up. Right, so I just opened up Google Collab, and there seem to be a couple of things that are already set up here. So it seems like on this account, not this account that not on the account that's on the machine that I'm streaming from right now, but rather the account that's on the machine that I'm currently not streaming from, the machine that I'm currently looking up Google Collab on. It seems like I have done I have looked into Google Collab on this machine, and I just forgot about it. I think, okay, so there's the Gemini API here. So I think maybe it might have been one of the two. It might have been so okay, it mentions the Gemini API, so I think maybe it might be um the Kaggle 5-day course. Though I think the 5-day course didn't involve um Google Collab. I think that so that was the Kaggle 5-day Gen AI course, and they were teaching various things about Gen AI involving, including, I believe, fine tuning. But they were explaining, a good bit about Gen AI in that. Um, I was supposed to go through that course, but I never managed to get around to it. I don't know what this notebook was for. So I just opened up collab.research.google.com and it directly jumped into this notebook. Oh, maybe this is just their way of this is sort of their welcome page. That could be it. This might be their welcome page. And let's see in their resources, what do they have or what is offered to you? AI Assistant, Collab Pro, GitHub. Okay, you know what? I'm not gonna get too distracted with this. What we're gonna do is continue learning about Google AI Studio. And by the way, there's a quick thing that I want to check out. I'm not going to check it out on stream right now, but I saw this thing before I started the stream, so I want to check this out. Apparently, somebody has made um, a real-time VTubing tool that uses AI to do well. I mean, in general, AI is used in the background, but they have created a VTubing tool, which I haven't looked into it too much, but I'm assuming it can it takes your real video feed and then applies that, or not applies that, but generates AI video out of it, of you talking. I think it's a little more than just applying. I think it's a little more than just capturing the landmarks and then doing calculations and applying that to a rig. I could be wrong. I want to explore this more. This, I believe it's called Warper. I think so. I think. I'm not sure. Or maybe the person is called AI Warper. I'll find out what their app itself is called. But yeah, this is something I wanna explore. They have the thing hosted up on Hugging Face. Okay, so um yesterday we got done with the Google AI Studio Quick Start thing, and we learned a bit. We learned a bunch of things. Also, I hold on. I just remembered yesterday after we got done fine tuning the model. I never tested it. The model is just here. I'm gonna do something real quick for which I need to switch to BRB. Now, give me a second while I try to use this. There's a button here that says use in chat, and then there's another button that says add API access. So I think we might be able to use this model. They might generate like an API key, and through this key we would be able to use the. Oh, okay. I did not think about that. Hold on just a second. Let me see where the thing is. Tuned models. It's under that. Okay. All right. So clicking on right, I can do that again here. So we click on my tuned model. This is the model that we fine-tuned on one of their pre-existing data sets. And then we have two options here. Maybe I could also wait. What is this going to? Model tuning tutorial. I think I'm already on. Okay. So then we have two options here. I'll use this option later on. For now, we can click on use in chat, and then that brings us to create prompt, the create prompt page, and that's basically this. So the model can be selected from this list if we just go to create prompt. What's interesting is the options here are kind of limited in terms of what you can do, which I guess that's fair because we were using a different model. We weren't exactly fine tuning um, we weren't exactly fine tuning something like Gemini 2.0 Flash. We were fine tuning, I don't know if it's listed here. I'm not sure if it's listed here. I think it was a smaller model that we were fine tuning. Let me try. Okay, let's click on tune a model, and then here we were fine tuning this Gemini 1.5 Flash. This. Let me Google this model. Gemini 1.5 Flash 001 tuning. Okay. Fine tuning is a process that can, yeah, okay. Cool, cool. I'm looking for information on that specific model. Okay, let's take a look at the fine tuning guide and see if that mentions anything. Now, uh, where was I? So here we finished this, right? And it's great that it's great that with the model we get two options. One is to use, hold on. One is to use the model in a chat, which will make us use it within, this UI. But then we also have the option for an API key. So we could have our model hosted on Google AI Studio, and then through the API, we can, or through the API key, we can access it from our own external programs, like from like a Python script or something. What was I gonna do? Oh yeah. Um, Give me a second. Okay, so from here we have two options. One is to go to the API side, which will start teaching us how to do stuff through the API, which I very much want to do because there's quite a bit. Actually, all of these examples, at least from what I've seen, all of these examples they're using the API. So like they teach you how to do these specific tasks through the API. And we're gonna go through a couple of these. I don't think we'll go through all of them because like we'll get the idea by doing a bunch of them. For the time being, I'm very much interested in these four. Thinking, I mean, we can look into that later. Oh, I'm interested in structured output as well. Oh, there was another one called function calling. I wanna look into function calling as well. You know what? Okay, we can explore a bunch of them. Uh, yeah. So from here we have two options. One, we can either dive into the API, or we can learn how to design prompts. And I feel like there's quite a bit to learn in terms of prompt engineering. At least for me, there's quite a bit to learn because uh, being able to being able to craft the perfect prompt, it can be the difference between getting low quality output and getting really high quality output. It can be the difference between the model just not doing what you asked it to do, or doing a very bad job of what you asked it to do, versus doing just a perfect job because you've prompted it properly in a way that it understands. I feel like, okay, prompt engineering is kind of interesting because I need to find out if um if the same prompt engineering guidelines and principles can be applied to all LLMs, or would it depend from LLM to LLM? Because each LLM has a different sort of design. They aren't all designed the exact same way, right? So I wonder if each of them has their own specific ways that they're expecting prompts, or if this is like a general, it's a set of general guidelines that you can apply to all LLMs. That would actually be great, because just learning in general how prompt engineering works, and just getting general guidelines, that would also be incredibly helpful. And then, depending on which LLM you're using, learning the specific prompt engineering principles of that LLM can also be, it can further be helpful for you. But yeah, I would be super happy if whatever we learn here can be applied to pretty much any language model. Um, okay, you know what? You know what? Wait, what is context caching? I'm kind of interested in this. So, you know what we're gonna do? We're gonna learn prompt engineering today. I think we're gonna focus on that. Um, because I feel like we're gonna get to learn quite a bit about how these LLMs work, how they handle input, how they process the input, and also what kind of output they give, and why they behave the way that they behave. Um, though I'm still not entirely sure if what we are learning here in terms of prompt design and prompt engineering can be applied to all LLMs. It can definitely be applied to Gemini, and probably future Gemini versions as well. And it'll help me get the most out of Gemini, which since I'm using Google AI Studio and I'm using the Gemini API and all, obviously I'm going to be using Gemini, so I want to get as much as I can out of it. No, you know what? Okay, this is a good question to ask another LLM. So let's restart this, or refresh this. Oh, sorry, zoned out. Okay. Uh, what was I gonna do? Yeah, I'm currently learning prompt engineering for Gemini. I'm wondering if the same set. I'm pretty sure the answer to this is going to be yes and no, because some of those principles can be applied, like to multiple LLMs, just because of how LLMs are in general. But I think certain points might be specific to specific LLMs. Um, if the same, I'm wondering if the same uh, set of prompt engineering principles can be applied to all LLMs regardless of their design. Because it seems to me like each of these LLMs share share a common design to a certain extent, even if they have a bunch of things added on top of them to make them special in their own way. Now, while this is actually, I think the answer is going to be pretty quick. Yeah, there it is. Okay. Okay. Let's tackle this question about prompt engineering principles across different LLMs. The user is learning prompt engineering specifically for Gemini, but is curious if the same principles apply to all LLMs regardless of their design. They think that maybe the common underlying design allows for shared techniques, even with each model's unique features. Okay, cool. First, I need to recall what prompt engineering involves. It's about crafting effective inputs to get the best outputs from an LLM. Common principles include clarity, specifying the desired format, providing examples, iterative testing, and so on. Okay. Um, Now, the user is asking if these are universal across all models. I should start by affirming that many principles do transfer because most LLMs share a similar transformer-based architecture. Okay. Uh, they're all they all process sequential data and predict the next token. So basics like being clear, using context, or breaking down tasks might work across the board. But then I have to think about the variations. For example, models might differ in training data, size, fine-tuning, or added features. So while a principle like clarity is universal, the way to achieve clarity might vary. Maybe Gemini handles certain instructions better than another model, or some models are more sensitive to prompt structure. Also, some models have specific capabilities, like some can access the internet, others can't. So, if a prompt relies on real time data, that's only possible with certain models. Similarly, models might have different max token lengths, affecting how much context you can provide. Hold on. Models might have different max token lengths, affecting how much context you can provide. Okay. Multimodality is another factor. If Gemini can handle images and text, prompts for it might need to include both, whereas a text only model wouldn't. Sorry, zoned out. Okay, what was I saying? Um, I think I was in techniques for those multimodal models would be different. Then there's the user's experience level. They're learning, so maybe they need to know that while core principles are shared, adapting to each model's strengths is key. Examples would help. Like maybe in one model you need to be more explicit about steps. Another might handle implied steps better. That's fair. Yeah. Also considering model specific be also what? Also considering model specific behaviors. For example, some models might default to a certain tone or structure unless instructed otherwise, so adjusting prompts to specify tone could vary in effectiveness between models. I should structure the answer into sections: universal principles, model specific adjustments, and practical tips. Emphasize that foundational techniques are transferable but need tweaking. Okay. Mention checking model documentation for unique features, testing prompts across models, and using examples. All right. Potential mistakes to avoid. Assuming all models react the same way to identical prompts. Okay. To a certain extent, I did make that mistake. Like initially, I was like, I hope these principles can be applied to all models, to all language models at least. But then I was like, yo, I don't think that's going to be the case because each of these models is unique in their own way, whether it's a big model or a small model or a multimodal model or just a single mode model. They're all unique in their own way, and each of them excels in different things. So, like because of that, I don't think you'd be able to apply all of these principles um, to all the models. Like you would need to certain principles would be a little different. They would need to be applied in different ways. But there are certain principles that yes, they could be applied to all models mainly because of the underlying architecture that they're built on. Where was I? Okay. Highlight highlighting that experimentation is crucial. Maybe mention community resources or tools that help tailor prompts to specific models. Summarizing, the answer should balance the shared foundational aspects with the need for customization based on each model's architecture and features. Reassure the user that learning prompt engineering for Gemini provides a solid base, but they'll need to adapt as they work with different models. Okay, your intuition is spot on. Um, Many prompt engineering principles are transferable across LLMs, but based on each there are nuances based on each model's architecture. No, not just architecture. Based on each model's architecture, training data, and unique features. Here's a breakdown of what works universally and where adaptations are needed. Okay, universal principles that apply to most LLMs: clarity and specificity. All LLMs benefit from well defined prompts that minimize ambiguity. For example, write a Python function to calculate factorial with input validation versus write code for factorial. Yeah, that makes sense. Contextual guidance, providing relevant context, example role playing, domain specific language, helps align outputs. Example, act as a historian, explain the causes of the French Revolution in 3 bullet points. Okay, iterative refinement, testing and refining prompts based on outputs, also called prompt hacking. Testing and refining prompts based on outputs is critical for all models. Structured output requests, explicitly asking for lists, tables, JSON, or Markdown often improves results across models. Summarize this article in 5 bullet points, use Markdown formatting. Okay. Breaking down complex tasks, chunking tasks into steps, chain of thought. Oh, that's called chain of thought. Okay. Boosts performance. First, explain quantum computing, then list its real world applications. Okay. Model specific adjustments, token limits, and. Okay, you know what? Hold on. I think. Yeah, I think we can move on to this introduction to prompt design. Okay, prompt design is a process of creating prompts that elicit the desired response from language models. Writing well-structured prompts is an essential part of ensuring accurate, high-quality responses from a language model. This page introduces some basic concepts, strategies, and best practices to get you started in designing prompts. Okay, what is a prompt? A prompt is a natural language request submitted to what? A prompt is a natural language request submitted to a language model to receive a response back. Uh, prompts prompts can contain questions, instructions, contextual information, examples, and partial input for the model to complete or continue. After the model receives a prompt, depending on the type of model being used, it can generate text, embeddings, code, images, videos, music, and more. All right, quick thing. In like 30 seconds, there's going to be an ad break starting. So I'm going to start the ad break right now, just so I don't miss the timer and then we don't know when the ad is going to start and all that. So I'm going to start the ad right now, the ad break, and I'll see you guys in 30 seconds. All right, welcome back. So, where was I? Yeah, it can generate embeddings, code, images. I'm interested in learning more about embeddings. We're not going to go too deep into it right now, though, because we have to, go through this prompt engineering thing. Give me a second. Okay, what are embeddings? Embeddings capture semantic meaning and context, which results in text with similar meanings having closer embeddings. For example, the sentence, oh yeah, now I remember. Embeddings are um, like a while back I had looked into it. Embeddings, they're like the numerical representation of, um, actually, no, I mean, well, okay, so I was about to say embeddings are like the numerical representation of the tokens, but I think I'm remembering wrong. I think because like there was a thing about vector embedding. I think I don't. Okay, you know what? Let's carry on with this. I might be remembering wrong. For example, the sentence "I took my dog to the vet" and "I took my cat to the vet" would have embeddings that are close to each other in the vector space, since both describe a similar context. You can use embeddings to compare different texts and understand how they relate. For example, if the embeddings of the text cat and dog are close together, you can infer that these words are similar in meaning, context, or both. This enables a variety of common AI use cases. Okay, right. So I need to read up more on embed. Okay, you know what? Yeah, let's do this. I'm learning machine learning. What are embeddings? Okay, there's quite a bit of information here, which is making me wonder if I should. Wait, what is this a link to? TensorFlow embedding projector. Visualizing embeddings. Wait, aren't embeddings usually like multidimensional? That would be interesting seeing how it gets visualized. Okay. Right. Um, okay, the user is learning machine learning and wants to know what embeddings are. Let me start by recalling what embeddings are. So, embeddings are a way to represent data, right? Like converting words or categories into vectors. But I need to explain this in simple terms. Maybe start with the basic idea that embeddings turn complex data into numbers that machines can understand. But why do we need that? Oh, right, because raw data like text or categories aren't numerical, and ML models work with numbers. Okay. I should mention that embeddings capture semantic meaning. This is a sentence that I remember. Embeddings capture semantic meaning. For example, similar words have similar vectors. King and queen might be close to each other in the vector space. Wait, that's the classic of example from word to vec. But I should also explain how they're used beyond words. Maybe images, user preferences, etc. Oh, right. Embeddings are used in recommendations, NLP, and computer vision. I didn't know that. I thought it was just like a text thing, like an NLP thing. The dimensionality aspect is important, reducing dimensions while preserving info. So, high dimensional data like one hot encoded vectors are inefficient. Embeddings compress that into lower dimensions. Training process. Neural networks create embeddings by learning patterns. So, during training, to the model em, the model adjusts embeddings to minimize loss. For example, in word embeddings, words in similar contexts get closer vectors. Applications. Mention recommendations. Okay, hold on. I feel like I should do research on this separately because you see how it's mentioned here, they might be close in the vector space. I need to figure out exactly how that vector space is being created, how the data that's stored within that vector space is being generated, like what is going on there. Defining key terms, vector. Oh wait, hold up. I think it's already answering the question for me. Applications. Okay, okay, okay. But wait, the user might not know about specific models. Maybe avoid jargon, but still give examples. Also clarify embeddings can be learned from any discrete data, not just words. See, I didn't know that. I did not know that. Um, Also, different types: word embeddings, graph embeddings, entity embeddings for categorical data, but maybe keep it simple for an introduction. Defining key terms: vector space, semantic relationships, dimensionality reduction, examples to illustrate, maybe compare to traditional methods like one hot encoding. Wait, the user is a beginner. So analogies might help, like how a map represents 3D world in 2D but preserves distances, or how a dictionary translates words into definitions but embeddings translate into numbers with meaning. Also, the difference between embeddings and other encodings. One hot is sparse, embeddings are dense and capture similarities. Okay, practical uses. Okay, potential pitfalls. Quality depends on training data, Biases in data can lead to biased embeddings. Need to structure the answer, define how they work, and so on, so on, so on, so. Okay, okay. User might check if the user might confuse embeddings with other concepts like encodings or feature extraction. Clarify that embeddings are learned representations specific to the task. Wait, also mention that embeddings can be visualized, like using so and so to plot word vectors in 2D. That helps in understanding the relationship. Now, putting it all together in a clear step by step explanation without overwhelming the user. Embeddings are a foundational concept in machine learning, especially in NLP and recommendation systems. Here's a straightforward breakdown. What are embeddings? Embeddings are numerical representations of data, like words, images, or categories, like in a continuous vector space. They convert complex, high-dimensional data, example text, into lower dimensional vectors of hold on into lower dimensional vectors of numbers that machines can process while preserving relationships and meaning. Think of an embedding as a translation of real world data into math. For example, the word cat, um, the word cat is a list of numbers. A user's music taste is so and so. Why do we need embeddings? Raw data, like text or categories, isn't numerical, but machines need numbers to compute. Embeddings compress sparse data, example one hot encoded words, into dense compact vectors. Semantic capture. Embeddings encode meaning and relationships. For instance, similar words have similar vectors. Relationships like king minus man plus woman equals queen emerge in vector space. Okay, I didn't get that example, but okay. Generalization. They help models learn patterns. Example: Paris is to France as Berlin is to Germany, without manual feature engineering. How are embeddings created? Training with neural networks. Models like word to vec, so and so and so learn embeddings by analyzing context. Words that appear near each other get similar vectors. Oh, so it's in the training data. The training data contains these sentences, and then in those sentences, it analyzes which words are close to each other. Though, how is it figuring out which words are close to each other? Dude, I just realized I could now ask these questions to Gemini because Gemini is much better at learning not learning. Gemini is much better at remembering context now. It can hold context for a much longer time. So I could start asking this question to Gemini through Google AI Studio, and I could use like what do you call them? Prompt instructions or system instructions or whatever to um, kind of dictate how the response is supposed to be given and in how much complexity the response should be given. Dude, now I can try that. Holy shit. I'm excited to test this out. Task specific tuning. Embeddings can be fine tuned during training for tasks like sentiment analysis or image recognition. Okay. Key properties, dimensionality. Embeddings are lower dimensional than raw data, reducing 10,000 dimensional one hot encoded vectors to 300 dimensions. Okay, that's crazy. Similarity. Similar items. I need to ask this question. Similar items. How are similar, how is item similarity determined? How does the the network know which words are considered close to each other? Okay, cosine similarity measures how close vectors are. Okay, I should look into cosine similarity. Transfer learning. Wait, I didn't realize. Hold on, cosine similarity. It can measure how close vectors are. I'm assuming that this goes way beyond just two and three dimensional vectors, because like in data science and ML we are often dealing with like hundreds of dimensions. Cosine similarity. Is there a thing in scikit-learn for cosine similarity? Because if it's measuring how close the vectors are, it's basically getting like a distance, right? In data analysis, cosine similarity is a measure of similarity between two non-zero vectors defined in an inner product space. Cosine similarity is the cosine of the angle between the vectors. Okay, right. Scikit-learn does have cosine similarity. Let's take a look at that. Compute cosine similarity between samples in X and Y. Okay, I'm going to test this out after the stream. Uh, right. And then here we went on to applications. Wait, there was also transfer learning. Pre-trained embeddings can be reused for new tasks. Example, word to vec from for text and ResNet for images. Okay. Applications: NLP, recommendation systems, computer vision, categorical data. Sorry, zoned out. Okay. Uh, right. Let's ask this question as well. Okay, there's quite a bit of information here. Okay, the user asked about how item similarity is determined in embeddings and how the network knows which words are close. Let me start by recalling what embeddings are. They are vectors that represent data in a lower dimensional space. So the core idea is that similar items have vectors. What? No, similar items have vectors that are closer to each other. First, I need to explain how the network learns these relationships. Probably start with the training process. Models like word2vec use context words to learn embeddings. For instance, words that appear in similar contexts get similar vectors. So the network adjusts the vectors during training so that the words appear together. Words, what? So that words appearing together have closer embeddings. Maybe mention the training objective. For word2vec's skipgram model, the goal is to predict context words given a target word. When the model does this, it adjusts the embeddings words that so that words that share context end up with similar vectors. No, hold on. Maybe mention the training objective, so and so skipgram model. The the goal is to predict context words given a target word. When the model does this, it adjusts the embeddings so that words that share contexts end up with similar vectors. Then talk about loss functions like negative sampling or softmax, which help the model learn by rewarding correct predictions and penalizing incorrect ones. Okay. Um, the model's weights embeddings are updated through backpropagation based on these losses. Visual examples help, like how king and queen are close because they're used in similar contexts, or analogies like king minus man plus queen equals queen. No, king minus man plus woman equals queen. Okay, I still don't get that. Okay, mention distance metrics like cosine similarity, Euclidean distance. Explain that cosine measures the angle between vectors. So even if vectors are long, similar direction implies similarity. Also, touch on how this applies beyond words to items in recommendations, like collaborative filtering, where user item interactions train embeddings, making similar items cluster. Need to check if the user knows about neural network basics. They mentioned learning machine learning, so maybe keep it intuitive. Avoid too much math, but mention key concepts like backpropagation and loss functions. Also, clarify that the network doesn't know inherently but learns through exposure to data. The structure of the task, predicting context, next word, etc., shapes the embeddings. Maybe mention other models like BERT, which use transformer architecture and capture more context. Different training objectives, but same idea of adjusting embeddings through training. Finally, practical examples would help. Maybe using embeddings in a recommendation system or semantic search, how measuring similarity works in practice. Okay. Um, okay. Great question. Determining item or word similarity in embeddings relies on the geometric relationship between vectors in the embedding space. Here's how it works. Wait, back up. Relies on the geometric relationships between vectors in the embedding space. Okay. How embedding captures similarity. Training objective. During training, the model adjusts embeddings to reflect patterns in the data. Words that appear in similar contexts, dog, puppy, both near fetch or bone, are pushed closer in the vector space. Items frequently interacted with by similar users, example in recommendation systems, are embedded closer together. Loss function. The model optimizes a loss function that rewards it for making similar embeddings for related items and dissimilar ones for unrelated items. Example, in word2vec, the skipgram objective tries to predict nearby words for a target word. Correct predictions pull the embeddings closer, and incorrect ones push them apart. Okay. Measuring similarity. Distance metrics. Once embeddings are learned, similarity is quantified using mathematical metrics. Common ones include cosine similarity, Euclidean distance, and dot product. Okay. How networks learn proximity. The model doesn't know similarity upfront, it discovers patterns through training. Sorry, zoned out. Okay. For word embeddings, uh, input a target word and the objective is to predict nearby words. Okay, predict nearby words. Oh, predict nearby words. So we that means we already have the expected output, right? Adjustments. If the model fails to predict France for Paris, it tweaks the embedding for Paris closer to France and farther away from irrelevant words. Over millions of sentences, words with over millions of sentences, words with so as you're iterating over millions of sentences, words with shared contexts cluster together. That would be kind of interesting to visualize. I feel like if I visualize that, that would be much easier to understand. The problem is, given the dimensionality of this data, you just can't visualize it unless like they have a specific way of a specific, albeit limited, way of visualizing this relationship, which they had mentioned something up here. Um, where was it? There was something for visualization. Hold on, there was definitely something for visualization that was mentioned here. I'm gonna find this later on. Um, yeah, here. Using TSNE. Let's take a look at that. TSNE. T distributed stochastic neighbor embedding. Okay. And this is a thing in scikit-learn as well. Great. Is there a way to visualize this though? Whatever is being given here. I'm not seeing a way to visualize it. Okay, I'll find it later on. There is a section on like embedding stuff in scikit-learn. Maybe at some point I should explore that. But yeah, okay. There is quite a bit of research that I need to do on this, and I'm gonna do that. Okay, now give me a second. Okay, um, I'm usually kind of nervous rating someone like with more viewers because I usually don't really have all that many viewers. Uh, so I'm usually kind of nervous rating in a chat where there's a bunch of people already. But I'm gonna try that. Okay. Um, because I usually raid someone that's within my viewership size. First of all, to support them as well, but also because wait, actually, yeah, okay, right. So we're gonna raid this person. This person is also chatting. This person is also talking. Their name is Pterodactyl One, and they are. I'm not sure what they're chatting about, but we're gonna go there. Okay. Um. Yeah. Yeah. That's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. I might do a mute stream later on, but considering that I'm rating this person, I'm probably gonna wait for like an hour or two before I do my mute stream, just so it doesn't look weird, because some people take that the wrong way. Um, but yeah, I have to go eat anyways, so I'll yeah, yeah. Um, yeah, yeah, dude. I'll see you guys next time. Peace.